Hi guys, today we are going to be looking at length, area, and volume with similar figures. So when we're looking at this, what we're trying to figure out is if we know that we have a scale factor k, or a to b, that relates lengths in similar figures, what will be the relationship between the area and the volume of these similar figures? Well, we know that normally this k value in a length will just be multiplied by the length to give us our end result. So here we have a length of 1 unit gets multiplied by a k value of 3 to give us 3 units in length. Well, in order to find out what could happen to area, we can actually start by just drawing a similar image and see what happens to the areas themselves. So I'm just going to start with a square. Let's say this square was 1 by 1 unit, and I multiplied it by the k. While I don't know how my area is affected, I know that in the end what will happen is instead of having a 1 by 1 side, I would have a 3 by 3 side. Now notice what happens then to the volume. Here area. Here my area is 1 times 1, 1 squared, which is just 1. And my end result is not 3 times as big, but it's actually 3 times 3 times as big, because we go from 1 to an area of 9, 3 times 3. So if I wanted to summarize that rule, instead of multiplying by k, all I did is I multiplied by k squared, because there was changes in 2 dimensions. So instead of multiplying by just 3, I multiplied by 3 squared. I can then record that rule. If I know my scale factor for length, I can actually find the area scale factor because it's just going to be squared. And we typically only call the length one the scale factor or the ratio of similitude. This, of course, will also apply to our ratios, so this would become a squared to b squared. And volume is actually affected very similarly. You probably guess already what will happen, but it doesn't hurt to visualize it. So let's say we started with a cube that's 1 by 1 by 1. When I multiplied it by that k value, I will now have a cube that has changed in 3 dimensions. So what I have is 3 by 3 by 3. Well, that means my change in volume is going to be going from 1 times 1 times 1, to 27, 3 times 3 times 3. 3 times 3 times 3, of course, is just 3 cubed, which means that all I'm doing to my k value is I'm cubing it from the original. And that general rule will follow. My volume will change by a factor of k cubed, the original scale factor cubed. And you can also write that as a ratio where you have a to the third, b to the third, using a and b from your original scale factor, or k. So what we want to do is we want to see how to use this. And this is actually really easy to use. You can use the length, area, and volume the same way that we've been doing length this whole time. And you'll know when you need area and volume when a problem does this. It will mention that figures are similar, and it will talk about different dimensions. So for example, in our first problem here, it says, in 2 similar figures below, so we know that they're similar, AB is 11 and VW is 5. And I can see that these are just lengths in my figures. So I'm going to mark them as lengths. I also see that I have an area of 20 units. So since I'm now dealing with a second dimension, I know I have to use these k values. And that gives us the base information to find the area of the other figure. The first step in any problem like this is to set up your k's. So I start and I just write k squared, and k cubed along the side, like so. I then fill in whatever one the problem gives me. So I can see that they've started by giving me a relationship between 2 lengths in the figure. Well, the one of these that shows me a relationship between lengths is just k. So I'll fill in k is equal to, well, 11 to 5. I can simplify that fraction if I want, or ratio if I want, but in this case it doesn't simplify nicely, and I'm just going to leave it like that. Now I know I want k squared because I'm dealing with area. I want to find the relationship between the area. Well, that means all I need to do is take the number above, my k value, and square it. So I have 11 squared to 5 squared. Here, that tells me this is the ratio that I will use to compare the volumes of the figures. So I'm going to set it up as a fraction, 11 squared to 5 squared. It won't matter which one you put on top, provided you stay consistent. Since the 11 belongs with the larger figure, that means that when you fill these in, the larger figure's area should end up on top. So here, I don't know the area of the larger figure, A, B, C, D, E, so I'm going to put that down as x. But I do know that the area of the smaller figure is 20, and so that goes on the bottom to match with my smaller length of 5 squared. Here, I can solve for x by cross-multiplying. Go ahead and try that out. You should find that x, that missing area, is 96.8 units squared. If you didn't, check your algebra by following along below. Don't forget that you don't need to square this 20 in our original ratio. And the reason why you don't need to square the 20 when you filled it in is because this 20 units is already in units squared. In other words, it is already squared. There's no change that you need to make. In fact, the only thing that you're ever going to be squaring or cubing will be your original k values. So let's try a little bit harder problem, going down to one that starts with this information. So again, I approach a problem like normal and consider what tools I have and what I will need to solve. So suppose that we have two similar cups. I know I'm going to be doing things with similar figures, so probably going to be working with K. One can fit 8 milliliters and the other can fit 32 milliliters. And when I think about milliliters, milliliters are just talking about how much liquid can go into an object. So we're really talking about filling this object with water or some other substance. So because I'm talking about filling something, what I actually have here is volume. Now that's fine because volume, of course, can be related with similar figures and scale factor. But see how the question here is asking first about height? It gives me a height and asks for another. And my second question here is asking about area. Because we're working in multiple dimensions, I know right away that I need to be working with k, k squared, and k cubed. Now this is where it can get a little tricky, because even though I know my initial setup is going to use k, k squared, and k cubed, unlike last time, the ratio that it started out with, or the relationship that it started giving me, is actually in volume and not in k, our normal scale factor. That's okay. I can still write this out as a ratio of 8 to 32. I just have to watch that I'm filling in my k. Notice that I don't cube these numbers because milliliters are already a cubic sort of unit. They're already dealing with volume. So now what I need to do is I need to figure out what k and k squared will be because I'll need both of those. Now regardless of what it asks, think to yourself, like, what can I find next? I don't currently have anything that allows me to go from a cubed to a squared. You will, of course, be able to do that if you know your algebra real well, but it's actually far simpler just to go from k to the third down to k. And I can do that using the cubic root of the number. If you have trouble finding this on a graphing calculator, don't forget that your cubic root can be found underneath the math button. So you can go over here into math, go down into the 3 and then the root sign, and type in your numbers. Of course, you probably already know that the cubic root of 8 is 2, because 2 times itself 3 times is 8. 32, however, is probably a little bit more obscure, so once you type that in, you should get 3.17. So that's our k. And if you have k, you can always find any other k value, because k squared, or area's ratio, will be 2 squared to 3.17 squared. Now I know which ratios to use. I just match them to the problem here. So the first problem is asking about height, which is the score of length. So I'll use my k value of 2 over 3.175. Remember to take a second to note which one's the smaller and which one's larger. It doesn't matter which you put on top, provided you stay consistent. So here, the height of the smaller cup is 20 centimeters. So next to my smaller number, I'm going to write my 20 centimeters. And I want to find the height of the larger cup. So again, next to my larger number, I'm going to put my x, so it stays in the same position. Then you cross multiply to solve. This is actually a pretty easy one since you're essentially multiplying by 10, though you can go the longer route. It should give you an answer of 31.7, and just make sure that you're using the right units. We are in centimeters for our final answer. We can do the same sort of thing with area. Since I'm dealing with area, I'm going to be using my k squared. So I have 2 squared over 3.17 squared. Of course, you can actually square these. I prefer just to leave them like this, just so that I don't make the mistake of grabbing the wrong one and not double checking my units should match what sort of power I have here. So the area of the base of the larger cup is 60 centimeters. Again, take note, larger. So my 60 is going to match up with the larger of the two numbers over here, which is on the bottom of my fraction, though it might be on the top of yours. And I want to find the area of the base of the smaller, so I'll put an x there. Here I can cross multiply and solve just like normal. When I do that, I get an x value of 23.88, and again, just check your units, centimeters squared. And that's it. So, long and short, or the short of it is, when you are dealing with multiple dimensions, write out your k, k squared, and k cubed. You'll know which one you're using based on whether you're in the first, second, or third dimension. And that is all.